Hello everyone, welcome back to the machine learning series. Today we are continuing with our discussion on Lasso, Ridge, and Elastic Net. As per in the previous class, we basically had a discussion on bias variance. Instead of we had a discussion on regularization. So we also introduced the concept of L1 loss and L2 loss, basically Lasso and ridge regression, right? So this is what is a sort of the objective function for your Lasso, right? So this previously, right? So this previously was the objective function only for your linear regression. Yeah. Basically, you're just trying to minimize your mean squared error, correct? Now, what you have added over here is, so this is basically the penalty term, right? Your absolute value of your weight. See, in some cases, weight is represented as beta. In some cases, weight is represented beta. It's nothing but a variable, right? So what does a variable denote? These variables denote weight values, okay? So this is beta, and these are the values of weights, right? So lambda is again a tunable parameter. Okay, so more on lambda later, but this is what is your objective function for your lasso regression. What you're basically trying to do over here is you're basically trying to minimize this. Okay, so this is what is lasso. Coming to ridge, so what happens in ridge regression is you're basically, instead of taking absolute value, you just take the squared value of this. That is the only difference between your lasso and ridge. Obviously, the way in which you are trying to minimize this, all of this differs, but the basic idea is this, right? Your penalty term would be squared value of your weights in ridge regression, and it'll just be a normal absolute value of weights in your lasso regression. So what we'll do is now is we'll just have a look at we'll just download one data set, again open source data set. We'll have a look at how it actually works on linear regression. We'll have a look at the coefficients of linear regression to see basically how the coefficients are without any penalty, without any regularization. And then apply Lasso, will apply a ridge, and when we actually see firsthand how does it actually cause shrinkage or reduction in your penalty terms. Okay, so this is again a sample crime data set. You have around 128 odd columns. Uh, each column has different attributes. For now, I think you need not worry about what does each column mean. So our main focus is only looking at how a lasso or a ridge causes reduction in the coefficient values. Okay. So again, these are very just basic cleanups. Right? I'm just dropping these many columns. I'm removing any. So this is the final data set. Okay. So we have a data set with 319 rows and 123 odd features. Okay, so this I'm defining my X and I'm defining my Y and splitting into train and test. I'm splitting into train and test. Okay, so I think this looks like this seems to be a previous version. So now when you say it's module named sklearn, so from sklearn, so we can just from sklearn. I think this was a previous version. Experimental features selection, kernel logic matrix, model selection. From model selection, import. Yeah, so I have the imports is done. So this was, I think this was previous version. X-train and Y-train. Now this way, just importing a linear model. So this is how you usually run sklearn. You just sort of import the class, create a model object, create a sklearn model object, then use fit method to train the model. Right now it's done. These are the linear regression coefficients, correct? Yeah. So right. So you have since you have 126 columns, you'll have 126 coefficients, right? Okay, so you have you have 122 columns. You have 122 columns. You have 122 coefficients. Again, this how do you easily understand this? Is think in terms of the gradient descent example which you saw, right? Where in I think in the very beginning of the machine learning series, we saw an example where we actually calculated the value of gradient descent through code, right? You took partial derivative for b and m, if you remember, right? or they took just BNM. Now imagine, so this is actually is what a real world example is. Real world will not be having just two variables, right? You'll be having hundreds of variables, right? In this particular case, think of where you'll be having 120 partial derivatives to be calculated, right? And that too in gradient descent. To get one update, right? To get one update, you basically need to loop over you need to go through the entire data set, not once, twice, but in this particular case, 126 times. You need to get 126 partial derivatives to get one update. Yeah, so that is what actually happens in an actual gradient descent. That's why the issues drawbacks with gradient descent. Okay, coming back, these are the different coefficients. These are different weights. We'll do the predict, ypred. These are the predictions. Now we'll look at it's actually how well it's actually performing. We are using root mean square error as error metric. Okay. In case you're confused as in which error metric to choose, right? So you have a bunch of error metrics. You have mean squared error, you have root mean squared error, you've just squared error, right? So we actually, I think in further classes there is a separate session on which error metric to choose, right? So which error metric works well under what conditions, right? Obviously you can't randomly choose. So there are certain sort of principles, certain guidelines which will help you in choosing. Which help you in choosing which error metric to choose. Okay. Yeah. Coming back. So this is now you've calculated RMSE. You calculate RMSE for a linear regression. So this linear regression is algorithm with no regularization, just your plain vanilla linear regression. Right? Now, basically, what we'll do is we'll basically run a ridge regression example.